Hi everyone, so in this video I'm going to go over something called ruling out chance. We want to rule out chance because chance is something that can just happen on any given day. We want to look for things that are called statistically significant. Something that is statistically significant is the likelihood that a relationship is caused by something other than chance. So usually it's caused by something that is in a treatment in an experiment. So when we look at something that is statistically significant, it is not because of chance, not because of something random that would have happened any given day of the week. It's because you put some sort of treatment on that experiment, on that subject in the experiment. We use randomized testing to do this. What randomized testing is, it's dot plots that we're going to analyze and see if something is very rare on that dot plot. And we're going to look at one in the next slide. So the scenario that we're going to look at in this whole lesson is randomizing a group of means. So we are given 10 tomatoes varying in shapes and sizes. These 10 tomatoes have been a part of a nutrient experiment where the application of the nutrient is expected to yield a larger tomato that weighs more. All 10 tomatoes have been grown under similar conditions regarding soil, water, sunlight, but 5 of the tomatoes received the nutrient supplement. That's your treatment. Using the weight of the 10 tomatoes, you wish to examine the claim that the nutrient yields larger tomatoes. So we want to see if using the treatment is going to give me a difference in the group means, the weight of the tomatoes. So it asks you, why would it be important for this experiment to be of all the same variety and grown under the same conditions? And this is because we want to eliminate any outside factors. Put an extra I in there. Okay, so you want to eliminate any outside factors that may sway making a tomato larger. We want to make sure that anything that's happening with the tomato is because of the treatment. We don't want anything else, different types of tomato, different types of soil, to impact the size of the tomato. So in this scenario, picture the circles as tomatoes. And it asks you, imagine that someone is assisting you using a random number generator and randomly puts these tomatoes into 2 different groups. So these are group A right here, and this is group B. So it says confirm that the mean is 6.76 ounces. All you're going to do is add these all up and then divide that sum by 5. And so when you do add up 9.1 plus 7.7 plus 7.3 plus 5.9 plus 3.8, and you divide that by 5, yep, you do get 6.76. Then they ask you to also find the mean for group B. So I'm going to add this all up and divide by 5, and when I add all those up, I do get a mean for group B of 6.48. Then they ask you to calculate the difference. This is a formula in statistics. It's called the Diff value. It's the mean of A minus the mean of B. So all you're going to do is take the means that you just got, so 6.76, and subtract 6.48, and we get 0.28. Now this means that on average, group A has a larger mean. Okay, and that makes sense because this value is positive. If we had a negative value, it would say that group A has a lower on average value by whatever this value is. So the diff value can obviously be different depending on the scenario that you are dealing with. So if I had a diff value of 1.6, that means that the mean of A minus the mean of B would give me 1.64. What this means is that group A's mean is 1.64 bigger than group B. Very simple, nothing major. If we got a diff value of minusing A from B, well, B from A, I'm sorry, and got negative 0.4, this would just mean that group A's mean is negative 0.4 less than group B. Nothing crazy here. But what if you got a difference value of 0? That means that you would subtract A and subtract B and get 0. Well, the only way we can get 0 is if you subtract the same exact average. So that would just mean that group A's mean is equal to group B's mean. And there's another scenario here, which they ask you to calculate group A's mean. So if I add up all these numbers and then I divide that sum by 5, I would get a mean of 7.84. If I add up all these numbers and divide that sum by 5, I would get a group B mean of 5.4. They then ask you to calculate the diff value, so if I subtract A and B, I get 7.84 minus 5.4, which calculates a diff value of 2.44. And this again tells us that group A's mean is 2.4 larger than group B's mean. Again, another scenario that we're going to use. So let's find the means of the two groups. So I'm going to add up all of these numbers, divide that by 5. When I do that, I end up getting a group A mean of 6.62. And I'll do that for group B. Add up all these numbers, divide by 5. That would get me another value of 6.62. So these two groups are evenly distributed, giving us the same exact means. So this just tells us that the diff value, when I subtract A and B, gives me a diff value of 0. So there is no difference in the average. It asks you then, using the 10 tomatoes, what arrangements would yield the largest diff value? So what would give you the largest diff value, and how would you get that to happen? Well, to get the largest diff value, what you would want is just to have the largest tomatoes in group A. So I'm going to pull all the largest tomatoes out. So that would be 9.1, 8.4, 8.0, 7.7, plus 7.3. If you put all those together and divide them by 5, you get the highest possible mean of 8.1. That means, by default, all the other tomatoes would be in the other group. 5.2, 3.8, in no particular order, just the smallest ones all together. 6.4, 5.9, and 4.4. Divide that by 5. You'll get a mean of 5.14. Sorry, I had to make this bigger. 5.14. And then they ask you to calculate the largest diff value. So if I do the mean of A minus the mean of B, and I do 8.1 minus 5.14, you would get a diff value of 2.96. Then it says, use your logic above, what would make the most negative diff value? All that would do is switch the tomatoes in these groups and flop them. So this means that group A would have a mean of 5.14, and group B would have the mean of 8.1. And when you subtract these two things of 5.14 minus 8.1, you'd get the same value, but obviously negative 2.96. So that just means that group B's mean is bigger by 2.96. It says, recall the 5 tomatoes that received the nutrients were hope of getting bigger tomatoes. But what if the treatment was not effective? What difference would you expect? Well, if the treatment was not effective, say if you put the treatment on group A and not on group B, and I'll just put T for treatment, and what if we had no effect of the treatment? Well, that means that the means would be very similar or even exactly the same. So it should be close to 0 because no big difference would have been calculated. When a big difference is calculated, this kind of means that the treatment might have worked, and that's something we want to analyze. So the best way to analyze whether or not a treatment works is to do that treatment experiment many times, and that's what we do in statistics. But usually due to money costs of an experiment, statisticians, what they do is they make distributions and they make things that are randomized by a computer. It's generated by a computer usually. So let's just read what this says here. It says, even though the difference of 0 could be some variability, this means that it is important to examine the entire distribution of different values. So where does it say? You can use a simulation. This is where it kind of tells you that you're using something that is simulated by a computer. So what this is telling us right here on the dot plot is that we did this 247 times. We already have done it 3 times if you remember that we had 2 groups of tomatoes. So there's 250 diff values, which means there are 250 dots in total on this dot plot. You guys can kind of see it's approximately normal because of the bell curve that we got going on here. And it also tells you that each of these dots are 0.04 apart. So it says, given the picture above, what is the approximate value of the median and the mean? Remember, this is the balancing point of the distribution. So that kind of seems to be around 0. So we would say about 0. And this does it imply no difference? Yes. It implies no difference because it's close to 0. So now we're going to really calculate what this diff value means. If something is considered statistically significant, it is rare to happen. So it really shouldn't be happening in this bulk of the dot plot. It really should happen towards the tail ends of it, because that's where we start seeing something statistically significant. If you think about the tomato weights, if you're here and the tomato weights of the 2 groups, the mean A minus mean B, was close to 0, the treatment probably would not have any sort of effect on the tomato groups. But if the tomato groups had some large difference between the means, they probably would be towards the tail ends of our distribution and tell us that there is indeed some sort of thing that is making this difference become so large. So maybe that is the treatment. So we do this by calculating probabilities with the dot plot. So I'm going to find a diff value, the probability that a diff value is greater than 0.28. That's out of 250 dots. 0.28 would be, let's zoom in here because it's a tiny dot plot. Because it's going up by increments of 0.04, it would be 1, 2, 3, 4, 5, 6, 7. So right about there, 7. If you count all the dots from here on, let me get a highlighter. From here on, that would calculate if it's rare or not. So I got 96 dots, so maybe I'm right. There's a lot of dots there. I'm pretty sure I'm right. I did it a few times. You guys can count from that point on and see if you get something different, but no matter what, it's going to be a pretty large probability, 0.384 is what I got. What if I did a probability of difference of greater than 2.44? Okay. That means I would go to 2.44, and if you guys can see, 2.4 is right there, and there is one lonely dot, 2.44 right there. So that is 1 out of 250. That's my probability of getting that, 1 out of 250. So 1 out of 250 gets me 0.004, very small probability of happening. Okay, 0 or more. That means we're going to count the dots from 0 all the way up. So that would get me, I counted 120 dots. I mean, you guys could maybe count differently. I'd counted a few times, so I'm hoping I'm probably pretty close. And that got me 0.48, which kind of makes sense because that's the halfway point, and that does round to 0.5. And then the probability of negative 1.6 or less, so that means I would count at this point and to the left of that, and that would be out of 250 again, and I counted about 23 dots, and that would get me a probability of 0.092. So the ones that we want to really look out for are the low ones. B and D are pretty low. Those are the ones that we can kind of say, there's some kind of statistical significance maybe in the difference. And that's how these probabilities can help you in determining whether or not an experiment's treatment is working really well. The other thing I want to kind of say is when you calculate a diff value and you calculate the probability, if you noticed for A and B, it had or more because those were positive values and they were on the right side of the tail. If you notice for the negative 1.6, it said or less, and that was on the left side of the tail. So that's really important to notice that when you have a negative number, you always count to the left. When you have a positive number, you always count to the right. The middle point doesn't really matter. They picked or more for this one. You could have done or less if you wanted. So the last thing we want to talk about really is how do you state statistical significance? And there is a rule of thumb. If you get a p-value of 2.5% or less, that's usually something that is rare and considered statistically significant. So would any of the diff values from number 13 be statistically significant? The only one that really makes sense is the diff value of, when we calculated the diff value, let me just erase this because I made a silly mistake. The only one that seemed really low was the one with the 2.44. So when we get the probability of the diff being greater than or equal to 2.44, we got 0.004, which move that over twice, gets you 0.4%. This is pretty small, so using a 95% confidence level, which is 2 standard deviations from the mean, this would be a value that seemed to be statistically significant because it's lower than that rule of thumb of 2.5%. And that's really it for this lesson. Basically, you calculate a diff value, and then you make a dot plot to see how it would look as a simulated distribution, and then you count how many dots there are above or below that value. And if there's not a lot of dots, that's considered something that is statistically significant, and that is something that a statistician or a researcher should really look into, because that value probably had the treatment really working. So I hope this helps you guys on lesson 105, and reach out if you have any questions.